and I would like to welcome Dr. James for the second part of the lecture.
Thank you. Thank you. I'm Mike. Thank you, and glad to be back with you again. Next week, you're going to have some of the real industry speakers, so things will really get going. So we talked last week about generally what the electronics industry had been like, evolving forward from where it started. And we talked a little bit about Moore's law scaling. Just to remind you, this is the law that Gordon Moore first observed back when there were only a few hundred transistors on a chip. That the number of transistors on a chip would double every generation, a generation being maybe 2 or 3 years. Every technology node would be the right way to think about it. And we're now up to the point where there's tens of billions of transistors on state-of-the-art chips, the highest performance chips. And we had our little, our exercise with a few volunteers, and I think our 3 volunteers last week tried to go more fine-grained than I might have really intended, but they were being good engineers in the process. But you know, we are carrying with us trillions of transistors in this room. Each of us probably carries a trillion or so transistors with us on an average day. So we started talking a little bit about how this happens. So we actually process full wafers, full silicon wafers. Those get processed in a massively parallel process. Once it's done, you would cut those wafers into what are known as die. These would be the chips that we talk about. Once a die is put in a package, it's generally called a chip. And a chip would be on the order of a millimeter by millimeter up to a couple centimeters by a couple centimeters, depending on what you're doing. But that's what we mean by die and chips and the like. So the next step, and I don't think we had time to talk about this last week, is you've got to package the chip into something. You've got to package that die. You don't walk around with a bare die and say, I've got a piece of silicon here. You actually package it into something. So there's a picture here on the top right, I guess, that's actually a transparent package. Most packages aren't transparent. This happened to be one that was used for getting light in and out, so it needed to be transparent. But you see actually in here, there's a die. That's the piece of silicon in the middle that has all these transistors and interconnects, everything on it. In this case, there's wire bonds. There's actually bond wires out to these outside set of leads. Then there's those leads actually get attached to the green printed circuit board. So you actually go from that die inside through wires out to a printed circuit board. And then the printed circuit board is what actually connects out to the outside world usually. The example on the bottom here is actually a memory chip. If you've ever added memory to your laptop or desktop computer, you actually bought something like this, a green board generally with a bunch of connectors on the bottom. It would slide into a slot on your main board, for instance. These black rectangles here are all the chips that go onto it. This would just be a memory chip. There's 4 of them. There's probably 4 on the other side of this board, probably. So that's what we mean by a die, a package, a board, things like that. So to make an overall system, if you buy your laptop board, if you open that up, if you look at the motherboard that's inside, say your smartphone, those are all die packaged into chips that get mounted onto a board that gets connected to the outside world through your keyboard, your monitor, your I/O device, whatever it is, right? So there's lots and lots of things these look like. The picture on the left is actually from a smartphone. You see, if you open up your smartphone and you ever have to change a battery, for instance, in a smartphone, the big device in the front, this is actually battery here. Get enough battery so you can carry around all day and not have your phone totally discharged, even though for some of us it doesn't make it quite through the whole day. And then the board, in this case, has been pulled out. This would be the main board, number of chips on that. Each of these black rectangles here is a chip that does something. If you look at a microprocessor, if you buy a processor for your laptop or desktop, that would be something that would look like this. There's a piece of silicon inside here. This is a metal cap on the top. On the back, though, you can start seeing a bunch of other components here. And all these things around the outside are all interconnect pins. Those are input and output pins. I can't count them right here, but you can see there's lots and lots of them. So now we have issues of how we get signals in and out of this thing. And that's the whole point of this package. It transmits all these signals from a socket on your motherboard into your actual silicon chip. So there's lots of different places we see them, lots of different things they look like. So one of the devices you're all quite familiar with is this thing that it injects sublime happiness into your ears, apparently based on these pictures. That's its main function. But if you open that up a little bit, This is just a picture I took off the web. There's happens to be a specific brand of ear pods. And if you look on this thing is all fits within about a cubic centimeter or so of space in order to be able to go in your ear. And there's actually a motherboard in there, the green motherboard. All these black rectangles are chips, packaged chips. And there's also some passive components like resistors and stuff. There's an antenna. Somewhere in there, there's probably a battery, so you can actually power this thing for some period of time. Okay. But since you're all now experts on this, we got an exercise table by table, so consult with your members around your table, and we'll ask you for some inputs in a couple minutes. But what needs to go in there? What functions do those chips have to serve to make your ear pods work? So go. Talk to people around your table. Make a list of, say, five key functions you think that those integrated circuits have to do. I don't know. What do you use an ear pod for? What do you use an ear pod for? Okay, does everybody have at least 2 or 3? Time to report in. So, elect somebody around your table with a loud voice to stand up and tell the group. Would anybody like to start? Just tell me one. Okay, right here.
You used to have a module, probably a Bluetooth module to receive and transmit data.
A Bluetooth module to receive and transmit data. So you need Bluetooth. Okay, we got that table. Let's go up here. You guys got one? Yeah, go ahead. Just one? Motion to sensor, so you can tell when it's not being used. Okay, good. Yes. Okay. Some feedback? Yeah, yeah, good. Digital into analog. Yeah, Bluetooth is a digital transmission. You got to get it in analog so it can inject that sublime wonderfulness into your ears. Yes. Active noise cancellation. Okay, good, good. That's great. Yes. GPS in case you lose your AirPods. Okay. Yes. A battery. Absolutely. You got to have battery. How about a microphone? Anybody thought about, you use these to talk also? You guys got it? Microphone and anything else to go with the microphone? How do you get from the microphone back into Bluetooth? Microphone's analog, Bluetooth's digital. So you got to convert analog into digital somehow. So you had digital to analog, but we also have analog back to digital. Anybody else? Something we missed? Yeah? A DSP? Yeah. Probably. Anybody like to tell me what a DSP is? Digital signal processor? Yeah. Okay, probably need one, yeah. An amplifier, so you can actually drive the speakers to hear the sound. Anything else we missed? Oftentimes you can I know it's kind of overlaps what you talked about before, but you can tap on it to change channels or fast forward or raise the volume. Some kind of tap on it. That's got some circuitry has to turn that into a decision, yes? Spatial audio? Okay. You guys already had several. Let's go on to some. Anybody else got one? Great. Okay, this is good. I like all these. So it does a ton of stuff, right? Somehow there's probably some charging circuitry for the battery also. You got to be able to charge this thing periodically. You don't want to go in and change a battery. We talked about the digital decoding and all that kind of stuff. I think we got most of all this. And note, you got to package all this, plus the speaker, microphone, and a battery, and an antenna, all within about 1 cubic centimeter. Okay, so everything we've talked about here would generally be classified as an application-specific integrated circuit, known as an ASIC, as opposed to a general-purpose integrated circuit like a CPU, a GPU, a microcontroller, et cetera. The difference being a general-purpose integrated circuit is something that, by software, when you open your laptop or tablet or phone, you can select an app and it will bring that in from memory, let you run lots of different apps, so it's reprogrammable all the time. So relatively speaking, we spend a lot of money on CPUs and GPUs, but they aren't particularly good at doing specialty purpose things. You wouldn't want to try to strap a GPU into your earbud and have it be reprogrammable, because it would chew up so much power you'd probably get a few minutes of battery lifetime out of it. It would probably burn your ear also. So you use application-specific integrated circuits because they can be much more efficient, low power, compact, et cetera. Okay? So what else do we have? We talked about Moore's Law, the fact that we're constantly putting more and more and more transistors on a chip. Well, chips aren't getting bigger. As a matter of fact, we want them to get smaller. So that means the transistors that we use actually have to get smaller and smaller and smaller. Every technology node as we move forward is a smaller and smaller and smaller transistor footprint. Okay? So we're currently, this very bleeding edge state-of-the-art node is currently 3 nanometers, which is 30 angstroms. We'll show a cross-section of a device in a second. But you need to have control of the line widths and processes within your fabrication process at this level. And I guess we don't really have it defined here, but these days the technology node is defined as the half pitch of the smallest interconnect line. So if you draw 2 of the smallest wires that are on the chip and figure out half of the distance between centers, that's the technology node we run at. Okay? 3 nanometers. And in order to do this, you start running in all kinds of fundamental limits. It turns out one of them is a lithographic limit. Professor Ronald Goossens, who was with us last week, is actually at ASML, is the company that builds the state-of-the-art steppers that do this. He's an expert at diffractive optics. But the basic idea is if you try to put light through a very narrow aperture, it starts diffracting out. If you've ever built a pinhole camera or during an eclipse, tried to image the eclipse on a solar eclipse, tried to image the eclipse through a pinhole in a car, see the image on the ground, those are all diffractive effects. And those same effects make it really difficult to focus and confine light at these extremely small size scales. So that winds up giving you a critical dimension or a minimum feature size you can make that has some coefficients out here, but the key is it's actually related to the wavelength of the light. So you wind up with a minimum feature size you can make that's proportional to the wavelength of light you use. And that's led in leading edge fabs to them using these massive steppers. I don't really have a picture that lets you see the perspective, but if there are humans next to it, the humans would look small compared to this big machine. This actually uses a wavelength of 13.5 nanometers. To put that in perspective, what your eye can actually see is around the range of 400 to 800 nanometers. So this is more than an order of magnitude smaller than the minimum wavelength you can actually see with your eye. Okay? And this is where leading edge fabs, companies like Intel, TSMC, Samsung, Global Foundries will buy these systems. Each of these steppers, if you're buying a state-of-the-art stepper, costs several $100 million just for that machine. These go into overall fabrication facilities that may cost $20 billion each to build. And so it's a field where it's hugely technology driven. It costs a lot of money to do it. And as we've sort of alluded to at the very bottom, you need very precise control, the mechanical, optical, thermal characteristics of these things. You need very tight contamination control. The reason these work in clean rooms is so you're not contaminating the chips with dust particles, which would ruin the whole chip. Yes? What's the theoretical minimum size? Well, it depends on what wavelength you want to run at. So these are 13.5 nanometers, and that lets you get down into that 3 nanometer half pitch. There's all kinds of tricks and games people play. So if you're willing to go to a shorter wavelength, you can keep going down. But this is getting extremely difficult, I'll put it that way. So the other thing that happens as you go forward is that transistor structures get more complicated. And I won't go in great detail with this, but the traditional way to think about a MOSFET was a planar device. It was actually a piece of silicon. This blue here is the silicon. You have a gate region. The green is a gate region. You would think about electrons flowing from the source to the drain in a planar structure. And notice that that's flat. That's like building a one-story building, basically. So in order to pack more and more and more transistors onto a chip, people had to start going vertical. Just as in housing, people go from one-story houses to two-story houses. You get into more dense urban regions, you start building 3, 4, 5-story houses. If you get into really dense regions, how many of you are from cities where you have 20-story or more apartment buildings fairly commonly? Yeah. You go 20 stories, 30 stories, 40 stories tall. This is how humans get more and more people per square mile into a city. Well, the same thing started happening a number of generations ago, a number of technology generations ago in the semiconductor field. They went to what are known as FinFETs. You started stacking the channel vertically. Instead of having a horizontal structure, you started having the transistor structure being stacked vertically this way, and now you would have current again going from source to drain. This allowed you to pack more transistors on the same footprint of area. Just like building a taller building lets you house more people in the same area. Okay? And nowadays, we're right at the cusp of moving from that into what's known as a gate-all-around structure. So now notice you got a number of these things stacked vertically. So these are the parallel channels that will stack vertically and all contribute together. So this is exactly analogous to multiple floors on a building, saying now we have space on multiple floors. So I won't, again, go into details, but these are actually extremely complicated structures to build. They're actually reaching atomic dimensions. This is actually from a research paper from Intel talking about a 6 nanometer gate length. So it's a little bit different than the technology node, but this is a transistor with a 6 nanometer gate length. Just to give you a perspective on what this is, the center region here is silicon. It's then wrapped in dielectric and then wrapped in a metal on the outside. And this cross-hatching you see in here is actually planes of atoms. So you're now down to the point where within a transistor structure, you can count the planes of atoms within the silicon channel. So you've all learned about atoms, you've learned about materials and stuff, but now we're literally at the point where these trillions of transistors that we're all carrying around with us have structures within them where you can count planes of atoms. It's fairly remarkable what the industry does. Okay? So we've titled this talk A New Era of Electronics, and let's talk about what that sort of means. One of the things that's happening is, in spite of the fact that Moore's law is still pushing more and more and more transistors in every generation, we're running out of computer capacity. The AI generation, for instance, is actually meaning that our need for new electronics is kind of going up faster than the actual amount we can produce. So Moore's law is remarkable. We can do more and more and more electronics all the time, bigger and bigger processors, things like that. But we're running into a mode where the demand for compute cycles is exceeding that. Those of you who read articles on, say, data centers and stuff like that, there's two big problems. One is the amount of power they're requiring. There's cities now that are running out of ability to supply power to these big data centers. And the other is just how do you keep building enough electronics to doing it? So there was a long curve here where this is the need for computing, how many teraflops of computing you need. And then about 2007, that started going up even faster. People started using deep learning and machine learning, and now we're entering an AI regime. You're reading the newspapers all the time. You pick up a technology section of a newspaper, of a magazine, AI is everything, and so that's demand for new electronics. So people are at the point, systems are at the point now where it's really what would be known as a system on chip. This is actually a Apple processor launched in 2023, so it's not that old. This one had about 67 billion transistors, but within that you have 12 cores of CPUs, 38 cores of GPUs, a 16-core neural engine. This was running on the TSMC 5 nanometer process, but all these things are on a single chip. You have memory, you have cache, you have the CPU and GPUs, you have the neural engine, and everything ties it all together. So this is really a system. It's got all those processors, all the cache, all the memory, all on one chip. So when you try to do it all on a single piece of silicon, it's known as a system on chip. This is getting more and more and more difficult. These are really complicated chips to build. It really makes it difficult to do these things. Plus, everything we said you needed on, say, earbuds, multiply that by at least an order of magnitude for what needs to go into a smartphone or a laptop or whatever else. And our volunteers up here last week trying to figure out what laptops you'd bought. They're asking me, how many of you have a GPU on your laptop? Well, a lot of people have GPUs. It's getting more and more difficult to do all those things together on one chip. So we're moving toward a new era where instead of system on chip, we're trying to do things in what's known as system in package. So the traditional way we thought about was you build a wafer with all the chips on it, you cut it up into individual die, you put that into a package, one chip per die, one chip per package. You then connect it onto a board and et cetera. And it's relatively low tech to do everything. Cost is a huge driver. This is why a lot of this packaging is done offshore. It's not done in the US. Now we're moving toward an advanced package where there may be multiple silicon die, multiple silicon chips within a single package. Here you see a complete system in package. This is a big package. You know, look at something you can barely hold in your hand, right? It's got lots of chips on it. You see two big chips here in the middle. You see a number of chips around the periphery. And that allows you now to put more functionality into this overall package than you could put into a single chip. And it allows you to mix things together. It's what's known as heterogeneous integration. So you could have one chip here that was really well optimized to be the main processor. You could have another chip here that was optimized to be, say, the RF system to do a cell phone connection. Now with 5G, 6G, we're going up to pretty high frequencies. That's difficult to do with silicon, so you do that with a different semiconductor material. If you do this heterogeneous integration, you can have different materials in these different chips and not be limited by those kinds of effects. So we're really moving in this era where people are doing what's known as advanced packaging, but an integral part of that is heterogeneous integration. How do you mix together processors, memories, high-frequency wireless devices, maybe optoelectronics devices? These days people are talking about optical interconnects even within your computing systems. So how do you do all that in an integrated way? And it's really the system in package that's allowing people to do that. So here's here's a diagram actually from our colleagues at SK Hynix. They're going to be building this advanced packaging facility here in town. In this case, it's an advanced package that has a multi-core graphical processor unit, GPU, and then a high-density, multi-level DRAM die stack, so they can integrate high-bandwidth memory here with the actual GPU. So this is how the most advanced GPU processors or graphics cards are being built. It's this idea of this heterogeneous integration, so you can put together the well-optimized high bandwidth memory, which is made with actually a different process than the actual processor core, and optimize both of those. And it requires you to put this on something known as an interposer, so this whole thing becomes packaged and then connects into the printed circuit board. And that way you can co-optimize everything, co-package everything, and get the ultimate performance. This is where the bleeding edge AI work is being done on co-integrated processors like this. So Moore's law is still going, even though it's requiring us to change the way we think about integration and packaging. But this will continue, and this will need to continue in order to meet that high demand for processors. So I want to say a few words about what the industry looks like. So you've all heard of a semiconductor fab, I assume. These are pictures from the net, but this is actually the TSMC complex in Arizona. One main fab building up and others starting under construction. Massive equipment. They actually run on robots. These things are all robots that bring wafers and mask reticles, the mask patterns, the mask structures in. So these things are zipping along tracks on the ceiling. They'll get to a given piece of equipment. They'll sort of drop down on cables, load the cartridge of wafers in, like an old jukebox kind of CD player or whatever. They'll run the wafers in, process, and then move on to the next piece of equipment. And you just have this whole array of pieces of equipment here. These are these $20 billion fabs we talked about. So that's what the industry would call a fab. It's a mainline fabrication facility. This is where the wafers are processed. Okay? And again, they're making 12-inch wafers as state of the art nowadays. So if you look at how you go all the way from end to end, how you start with a concept for a circuit and move all the way through to actually having a final package circuit, you could start with hardware design. That's where you would actually design, validate, test, and integrated circuit design. You would then tape that out. You would actually tape out the design into a set of masks and a set of process steps that could be made at a foundry or at a fab. You would then go to a fab. You would have them fabricate the wafers. The wafers would then probably go somewhere else to be tested and assembled and integrated. So you have that end-to-end of the hardware design, the fabrication, and the integrated packaging, whether it's conventional packaging or this advanced packaging, say heterogeneous integration. So if you would have been taking a class like this 30 years ago, the standard model would have been what's known as an integrated device manufacturer, where they have all those functions under one company. And they still exist, right? Places like Intel, Micron, SK Hynix, Western Digital, Samsung, TI, ON Semiconductor, NXP. They all do this. They have in-house that whole capability to design their own chips. For instance, the Intel processors that you buy are all designed. Most of them are fabricated still within Intel, but they have that end-to-end process. It's known as integrated device manufacturers, or IDM. What's happening much more commonly nowadays, though, is now instead of having all that under one roof, you have a whole array of things. What's really enabled this is what are known as foundries. So it's a standalone company like TSMC, Global Foundries, some of Intel's business, where they actually are just foundries. It's what's known as a pure play foundry, where they do the chip manufacturing, but they don't do the chip design. That's done elsewhere. So you have these companies that are known as fabless design companies, the Apples and Qualcomms and MediaTeks and NVIDIAs of the world. They do the chip designs. They then pass them on to the foundries. They're fabricated as wafers onto chips, and then they're sent off to an outsourced assembly and test organization to assemble them together. So this is the ecosystem. You have foundries, you have the fabless design companies, you have the assembly and test companies. To support those, on one end, you have the companies that build design tools. These are known as EDA tools. Companies like Siemens, Mentor Graphics, Cadence, Synopsys, they actually provide the tools you can use to design, the software you can use to design the chips. You also have companies that are supporting the foundries, the tool manufacturers like ASML, Lam, Applied Materials, Intel. They actually build those process systems that would go into a fab. And you have materials companies, Entegris, Air Liquide, Qnity is what was DuPont. They've just spun out their electronics materials division, so you'll see that now instead of DuPont. But these are the companies that provide everything from the wafers to the chemicals that are used, the materials and chemicals that are used on the way. So it's a really interesting ecosystem where it's all connected. It all works, but if you're sitting in a foundry, you receive these designs from the fabless design companies. You've been working with them probably on the whole design all along the way. You utilize machines that were built by these other companies. You bring in chemicals and other materials that are made by these companies, and then you send wafers out to the other end. So it's a whole ecosystem that's all connected together. They have a broad need for talent. We actually did an employer survey a couple years ago, and they hire people from all kinds of disciplines and majors, most fields of engineering, but also chemistry, physics, computer science, a lot of data science they need, industrial engineering, and they hired a lot of degree levels. They hire a lot of associate's degrees to do technician level work, but at the bachelor's, master's, PhD, they hire people to do both process engineering, integration, but also R&D, new process development. As we said before, this is an industry that lives on innovation, so they spend a lot of time innovating to try to keep all those next technology nodes working. The equipment companies are always innovating, the materials companies are always innovating, the chip design companies are always innovating, so it's an industry that lives on innovation. So the time I have left, I want to say a few words about semiconductors at Purdue. You're all part of it, whether you know it or not. You're all within semiconductors at Purdue because you're in this class. We have semiconductors at Purdue t-shirts that you will soon be able to buy if you want one. Details to follow. I think we have that all set up. But anyhow, so Purdue has what we think is the country's first large-scale semiconductor degree program. Established in 2022, it actually predates the US CHIPS Act. We have disciplines and options that are kind of addressing all those segments of the semiconductor industry, everything from chip design, actually EDA through chip design, all the way out to packaging, advanced packaging. People participating in the colleges of engineering, science, polytechnic, management. We have a campus-wide certificate in semiconductors and microelectronics. Sophie, who's one of your instructors here, actually kind of is the person to talk to about that. I'm sure we'll have more details. I'll be back at the end of the semester. We'll give you more details about that. But there's a campus-wide certificate. This class is actually one of the things you can count toward getting up the credits for that certificate. You can also count things like study abroad, corporate internships, experiential learning programs on campus. We have a list of about 100 semiconductor-related courses on campus you can elect. So it's accessible to all of you. It's campus-wide. We have departmental concentration in minors in 4 departments and a 5th pending. Those are generally, you take your core requirements in your home department and then you take a bank of 5 courses to complete the specific requirements. Many of these are also available as minors, so if you want to go take a minor in another department, you can get a semiconductor or microelectronics minor outside of your home department. This is all accessible to you. You can definitely sign up for these things. The Semiconductor Career Fair was mentioned earlier. We're actually going to have a briefing session for the employers before the career fair so we can get them all that terminology built up so they know when they see a student's resume what all those different programs are. We have some really strong experiential learning programs at Purdue focused on semiconductors. We have vertically integrated projects teams. Vertically integrated projects is a multi-university network of institutions on these programs, so actually co-founded by Purdue. These are multi-semester team design projects. You can work on them over multiple semesters. And definitely open to sophomores, but even in first-year engineering, there's some of these you can get into, especially some of the intro courses. The 2 that are really semiconductor focused are Socket, System-on-Chip Extension Technologies. That's a chip design endeavor. They've recently launched an Intro to Socket course to provide chip design fundamentals to new students, so you can take a semester or 2 of the intro course before you actually join a chip design team. They actually go all the way through to tape out in Socket, so you can be on a team that's actually doing chip design and periodically taping out a real design that will be fabricated at an external foundry. That's not unheard of at US universities, but it's kind of rare as an undergrad to be able to actually do chip design. The other thing we have is VIP at Burke, or oftentimes also known as Semiconductors at Burke. I never know quite which to call it. This is manufacturing and advanced packaging. It has teams on statistical process control, heterogeneous integration and advanced packaging, and a new team on digital twins. You're actually building essentially a physics-based virtual reality environment of a process tool. And we also have semiconductor-focused study abroad and or Silicon Valley trips. So those are also accessible, usually short-term trips, faculty-led, faculty staff-led, and focused on semiconductor companies. There's also a multi-university network headquartered at Purdue called SCALE, Scalable Asymmetric Life Cycle Engagement. It's undergraduate and graduate programs. They have technical verticals that are relevant to defense, aerospace, and commercial leap ahead. And in the past, this has been restricted to US citizens, but I believe they're trying to open it up. So if you're an international student, you can also participate. There's also, you've already heard about the call out for SSA. Purdue is the founding chapter of the Semiconductor Student Alliance. Some of our students have also created a nonprofit so they can support chapters at other institutions. So it's great to see that entrepreneurial bent in our students here. We're launching this semester a new student ambassadors program for semiconductors at Purdue. We just had applications in for that recently. And our ambassadors will represent us at corporate visits, events with student organizations, and the community. I should note that in addition to the Semiconductor Career Fair, we will have corporate speakers, of course, for this class for, 10 or 12 weeks during the semester. There's also will be a number of company at Purdue days, just like for those of you who walked past, just out here, I guess, over this past week. Caterpillar had a Caterpillar at Purdue Day. We'll have a number of those for semiconductor-focused companies, so pay attention. You can come by and get information and talk to them about future opportunities. Okay, so STARS. I have to cover STARS because half of you probably signed up for this class because you wanted to do STARS. So let me tell you about STARS. So STARS has run for the last 3 years, 2023, 2024, 2025, as a paid summer internship that was generally for rising sophomores. We had 2 tracks, the design track and a manufacturing and advanced packaging track. I've actually been co-leading the second track for the last 2 years. It's been really fun. Several of our students in the room have been through that. But here's the problem with STARS. This is, for the last 2 years, the number of applicants versus number of interns. So you can see this little red box up here in each case. That was the number of slots we actually had open. This big gray box was how many people applied to it. So we're turning down 90% of the applicants. So I can't look anybody in the room in the eye and say, look, you took this course thinking you'll be able to get in STARS, but you got a 1 in 10 chance of actually getting in. That's just not right? We can't keep doing that. So what we're going to do is morph this thing. We're going to morph this into a series of programs where you can get that content, you can get those experiences, but without being in the constraints of this 10-to-1 ratio. We'll probably still have some kind of summer programs. We're still working on that for next summer. But let me point out 2 opportunities that are definitely there. So these I can offer you right away. So we have the short course material from the first 4 weeks of STARS. The way both tracks of STARS worked was the first 4 weeks or so were kind of tutorials, or at least contained tutorials, to get you up to speed. The STARS design track had a 4-week boot camp on chip design, on digital design, and got you into actual chip design framework. And the semiconductor manufacturing, or the STARS track on manufacturing, had lecture material over the first 4 weeks to get you up to speed on manufacturing concepts. We're taking both of those packages of lectures and turning them into intro courses. So we already have an intro to socket course that's already up and running. So I think a 2-semester sequence. We're about to launch an intro to, it's co-listed. It'll be called Intro to VIP at Berk and or STARS Intro to Semiconductor Manufacturing. Again, it's the content from the STARS program, and that will be available pretty soon. Initially, I think on a NanoHub kind of course, but longer term as a credit-bearing course. And let me point out then, if you move from those into either socket or VIP at Berk, either one of those will take you well beyond what you could actually have done in the summer STARS program anyhow. So you have accessible to you a package of intro courses and then VIP experiential learning that will get you everything you would have done in the STARS internship. And I'm pretty confident we'll have much better ratios through those pathways. Okay, So just to finish all this up, semiconductors are pretty important. They're kind of out there in everything we do. They're actually strategically important for the US. They're getting more powerful, pervasive, and differentiated. Innovation is key to the industry. It always has been. I think will continue to be. Universities, I think, have a pretty important role to play, in part to train the next generation of students to go out there and be employees. And I think you'll hear over the next 12 weeks or so that there's lots of good career opportunities out there. I think the speakers that come in will tell you about what their companies do, what the perspective of the industry is, what the ecosystem looks like, and how you can participate. So I'll just refer you then to our webpage, our Semiconductors at Purdue webpage, where we have, I think, potentially useful information, even though there's still a few things we've got to fill in. So thank you very much for your attention. I think we have a few minutes where I'd be happy to answer any questions. Yes?
You mentioned earlier
Microphone's on the way.
So, okay. So earlier you asked, oh sorry, you didn't ask. You said that higher frequencies of light, basically lower wavelengths of light, makes it so that when you shine light through a hole, it's more accurate and you have more of a controllable dimension, right? But you said it was getting more difficult to decrease that wavelength. Can you expand on that?
Well, yeah, there's two things that go on. First of all, the 13.5 nanometers is what we used to call X-rays. Now it's being called deep UV or extreme UV because people don't want to think about X-ray systems. And X-rays are just hard to deal with. It's hard to generate them. When you hear the ASML lecture this semester, you'll really appreciate it. But the other problem is you can't use conventional optics. I mean, if you just think about a lens, a glass lens, like we would use for this, those don't work for X-rays. The materials we're used to using become opaque, and you got to go to all kinds of different things. So it's a tremendous challenge both generating those short wavelengths and steering the light, building good optical systems. I think there was one over here, and then we'll be back. Yes?
You talked about intro to socket. Is there any prereqs for that course?
Intro to socket? I think it's minimal prereqs. The assumption is you're coming in with sort of first-year engineering background, and you understand some basic coding. You've had a programming language.
Do I need to be in VIP to do it? Or
Well,
no?
intro to socket is a pathway to being in VIP, but you don't have to. I think you can take intro to socket and then stop if you want.
Okay.
Yeah, you don't. It's a way to get in. There's one over here in the corner, and we'll get back.
You said some companies are just found, some companies like Intel, they do everything on their own, but they also provide chip manufacturing for other companies. Like Intel might make chips for NVIDIA and stuff. What stops companies like Intel from using another company's chip designs? If they're also a foundry, or what stops them from knowing about that?
Well, the question is, if Intel both makes their own chips and serves as a foundry, what prevents them from using other people's designs? That's a huge issue, and I think that's something these companies struggle with. But Intel's also, I understand, making some chips at other companies' foundries. So I think they do all of those things. There's one over here we need to get, by the way. So yeah, that's an issue. But confidentiality, privacy, those are all issues they go through. Yes.
Earlier you mentioned that different semiconductors have different properties and that might make them better or worse for certain situations. Mm-hmm. So I've heard a lot about gallium nitride and how it's better than silicon in a lot of ways. It's more power efficient and you can package it more densely. Is there a disadvantage to that?
Yeah, so the question was other semiconductors besides silicon may have other advantages. The specific question was about gallium nitride. So gallium nitride is really good for two things. Light emission, so if you want to, as people went to different colors of LEDs, it used to be if you had a laser pointer it was red, and then you wind up having all these other colors of laser pointers. So materials, gallium nitride and related materials made that happen. And silicon does not emit light well, so you almost never see a silicon laser pointer. You just can't do it, right?
Right.
Silicon is extremely good for large-scale digital electronics. Nothing else can compete. Gallium nitride is really good for both the optical devices, like if you want to build a light emitting dot, or a laser pointer, but also for high power. So if you want high power, say RF, if you want a base station for transmitting out your cell phone signals, you might build that out of gallium arsenide or gallium nitride. It's not good for, it's not well suited for silicon. But silicon has this infrastructure to allow these 10 billion transistors. The other materials you're talking about, you would build much smaller circuits. You know, the laser pointer is one device. It's not 10 billion. Yes?
How do you see like either like quantum technology playing a role in transistor technology or like the other way around?
How do I see quantum technology playing a role in this? Well, I mean, these are quantum devices. I mean, the very first, 2D electron gas is actually a silicon MOSFET. So they're quantized devices in a large sense. But if you're talking about, say, quantum computing and things like that, I think for quite a while there will be quantum computers and silicon-based computers running side by side. I mean, quantum computers do some things really well, but they don't handle huge amounts of data. You know, they aren't going to be search engines, things like that. So you'll have to marry those two together. You'll have to use your CPUs and GPUs to do the big data, bring, if you do, say, global weather calculations or something. You have to have some way to pull in all this data and then crunch that into the quantum computer and let it do its thing and then spit something back out. So I think it'll be almost like a co-processor for some period of time. Yeah, we had a question back here.
You talked about advanced packaging or putting multiple chips in one package. Obviously, that increases the footprint of the package. So how is this being mitigated? Because obviously, like, if you're designing an iPhone and you want to have an advanced packaged thing in there.
Well,
Yeah.
so the co-packaging, the system in package, yeah, it increases the footprint of the package unless you stack three-dimensionally. So there are literally, like this, the GPU, the SK Hynix memory, they're actually vertically stacking memory chips. So you stack one chip on top, or one wafer on top of another, and then cut it up into chips, which cuts down the footprint, but then you've got a lot of heat to get out, right? So you all know if you've ever balanced your laptop on your lap, there's a lot of heat coming out of that, right? And so there's going to be a real heat problem for those of you that are going into mechanical engineering. Getting that heat out is a huge problem. So I think that'll be a big issue. Yeah.
Earlier in the lecture, you showed us a picture of a really small transistor, and you showed us how we can see individual planes of atoms. At what point does it get so small that like the interactions between the, like, basically, what's the theoretical limit of how small it could get based on, like...
What's the theoretical limit of how small a transistor could get? We saw pictures of individual planes of atoms. We're reaching those limits. There are fundamental limits. I mean, if nothing else, you got to keep enough layers of silicon that it behaves like silicon, enough layers of an insulator it behaves like an insulator. But that's one of the real reasons for this three-dimensional stacking. Because remember we said the real game was how many transistors can you pack in a square centimeter? As you start going vertical, now you don't have to make each little element as small. You can keep the element size the same, but stack multiple ones vertical and win there, right? So I think we're already kind of at the limit of how small you can make a basic transistor unit, that sheath of silicon we talked about. You just can't go down, you certainly can't go down below one atomic layer, right? One of the things that is under active research, though, is what is known as two-dimensional materials. Things like molybdenum diselenide and things like that, which, a single plane, well, it's a bilayer plane, but a single layer of this stuff is still a semiconductor. And that's kind of the fundamental limit. Think of a single plane of atoms or single bilayer plane of atoms being the unit. That's really promising, but it's going to take a lot of work to get there. Somebody else has a microphone over there. Yeah, go ahead.
I've heard about a process called zinc oxide casting when making chips. Could you please describe that?
What was the term in?
It's called zinc casting or zinc oxide casting, where they like blast that really small wavelength light through like a drop of zinc oxide, and that etches a pattern onto the chip.
Oh, okay. I'm not real familiar with that, so I can't really give you any insights. But when ASML comes, ask them. He'll know.
Thank you.
Okay. Yeah, way in the back. Go ahead and shout. This is the sub 10 nanometer nodes that. Are you asking about Intel specifically? Okay. Yeah. So, as they progress down in these nodes, going below 10 nanometers, it was reported. I can't tell you corporate secrets because I don't know, but in the literature, it was reported that Intel missed out on implementing one of the nodes. They fell behind there, which is a huge problem, and they were working hard the last time I read to try to catch back up, get back onto that node. But it's interesting because we talked about this fact that 30 years ago there were a lot of companies that had everything in-house, all the way from chip design to the actual fabrication and all that. And one of the reasons it dropped out is it's so expensive to build a fabrication line. You've got to keep it running 24/7. So you've got to have enough internal demand to keep doing that. And companies like Global Foundries decided not to push below the 10 nanometer node. They stopped at like 12 nanometers, but diversified out. So they do a lot of things with, say, silicon photonics, higher frequency devices, things like that. So it became the point where fewer and fewer companies could keep pushing that latest technology node. It was just too expensive to keep doing it. Okay, I think we need to wrap up. So thank you for your attention, and enjoy the rest of the class.